All right. So now that we understand PMD and PLCP and PSDUs and things like that, so let's go to 802.11b, which was DSSS, Direct Sequence Spread Spectrum, Complementary Code Keying. So this is called bits, which are what you are wanting to send. What goes on the medium is called chips. We already introduced that notation, right? Because each bit becomes a number of bits. In this case, in case of 802.11b, 11 chips per symbol. Each symbol is just 1 bit long. All right. Each bit becomes 11 chips. And then we use differential QPSK. So QPSK gives you 2 bits, right, per hertz. So you get about 2 megabits using 22 megahertz. How do you get 2 megabits? Because 22 megahertz, you get about 2 chips per hertz. 2 chips per hertz, right? So that gives you 11 mega chips per second. And then you divide that by 11. No, sorry, 22 becomes 44. Sorry, 44. And then divide by 11. I mean, by whatever. I mean, basically, so you should get 2 megabits per second. Let's just do that correctly. So you will get 2 megabits per second using 22 megahertz. Okay, so let's just do this one more time. 22 megahertz gives you 44 mega chips divided by 11 should give you 4 megabits per second. I'm missing somewhere a factor of 2. QPSK. Oh, okay, sorry. It is differential QPSK. It's not QAM. Phase shift keying, quadrature phase shift. I think you can only get 1 bit per hertz. Okay, QAM gives you 2 bits per hertz. QPSK gives you 1. So that is what they want. So 1 times 22 divided by 11 gives you 2. 2 megabits per second. Okay, and that was in the original 11. In the 11B, they used 8 bits per symbol and 8 chips per symbol. Okay, so now instead of 1 bit like this, they will take 8 bits and then translate into some other 8 bits using some code. Okay, so each symbol has 8 input bits as well as 8 output chips. So now you get basically, now you do the multiplication. 22 megahertz becomes 22 mega chips divided by 8 multiplied by 8. You get 22 megabits. Again, I'm missing a factor of 2. I'm missing a factor of 2. So you got 11 at the end, and now I got to figure out where the 11 factor of 2 is. But basically, using these numbers, you should be able to figure out, given how many bits per hertz you get, you should figure out that how many hertz you have, how many bits you will get. At the end, you will get 11 megabits. Okay, I will figure out that factor of 2. All right, 11A went on to better modulation. And it from BPSK, QPSK. Actually, here are the numbers. I am probably off by factor of 4. It says QPSK is 2 bits per hertz. So anyway, so basically OFDM. So 11A introduced OFDM. 64 subcarriers in 20 megahertz. 6 subcarriers at each end are used as guards. So basically 4 as pilots. So these are the guards. These are pilots in the middle. So you have about 48 for data. And so instead of 20 megahertz, you really have 12 megahertz for data, because out of 64, you have only 48, which is 3/4. So instead of 20, you have 3/4 of that. 3/4 of that would be 15. We have 60%. Anyway, so out of these, basically we get 12 megahertz for data. And using BPSK, you get 1 bits per hertz. That will give you 12 megabits per second. If you do half FEC, forward error correction, that means for every bit you send 2 bits, you will get 6 megabits per second net. On the other hand, if you send using 3/4, where for every 3 bit you send 4 bits, you will get 3/4 of this, which is 9 megabits, if you do half and so on and so forth. Okay. So one thing is that by multiplying these numbers, you should be able to get megabits per second. And you should be able to figure out how many bits per hertz there are, right? And then since the hertz is given, you can calculate the megabits and then the coding. Coding is these fractional codings. Basically, all you do is multiply and you get the rate. So 1/2 means 1 bit data, 2 bits sent. 3/4 means 3 bits data, 4 bits sent. So you add 1 extra, right? 2/3 means same thing, 2 bits data, 1 bit extra. Yeah.
So in the previous slide, that would be a 1 to 10 ratio?
1 to 10 ratio. Which one, 11 or 11B?
Look at in that picture there. You have 10 bits of signal.
11 bits actually.
Is that 11?
It's supposed to be 11. 0, 1, 2, 3, 4, 4, 8 to 10. I have shown 10, but they're supposed to be 11.
Oh, okay. It's supposed to be a 1 to 11. That's that ratio?
That is 11 chips per symbol. In the original 11, we had 11 chips per symbol. Now, this is not the ratio. Okay, let's don't confuse. Okay, hold on. So, let's just start with the bits alone right here. Okay? In fact, maybe even before this one. Right after the modulator, I have not shown it to you here. Whatever comes out, either before the modulator or just after the modulator, I'm not really sure at this point. We will add extra bits. That's the bits I'm talking about. FEC, error correction. Yeah, before the modulation, we will add extra bits. Yeah. Actually, I have to figure out where the error coding is. It could be, in fact, it could be even here, beginning. It could be anywhere.
Yeah.
Huh?
Yes.
It could be anywhere. But I think they have a particular place where they do it, and looks to me that the best place would be right in the beginning, right here. So somewhere they increase the number of bits. So instead of 2 bits, you have 3 bits. 2/3.
What does the error correction do? Is it just to like kind of water down the chance of an actual data bit?
Oh, error correction. So actually, I mean, again, okay, this is something 473. In 473, we teach about error correction, but I'm going to just give you an idea. So if I send an extra bit, then we can figure out whether the bits are wrong or not, right? But just parity bit. This is how the parity works, right? If the parity doesn't match, then we know that this is wrong. Right? Odd and even parity. And if you add 2 parity bits, then it can tell you more than that this is wrong. It could tell you that the second bit is wrong, and you can flip it and everything will be okay. That would be error correction. Right? So, but this is not, parity is not the end of, this is the beginning of the error correction. There's a whole course that can be done on coding theory, where they teach you how to get the best error correction with the minimum number of bits added. So here, there is more than this actually. It doesn't really show you. I mean, this is actually, see what this picture, even though it shows FEC, there is one more coding which is done, which is not shown here, Reed-Solomon coding, which will come up in the next lecture that we have, number 7, where we have multiple levels of these error corrections also. But for this picture as shown, you can calculate these numbers using these things. And actually, user never sees any of this number, by the way, because the user gets much less than this. Most of this is header and CRC and this and that, and RTS and CTS. By the time you bring down to the user sent, it will be 1/4 of it. Right? But at the physical layer, this is the bits you can get. By the time you come to the user layer, there is a lot of headers and things like that. Okay. So anyway, so few things from this slide, please. One is that you understand guard. You understand pilot. This is for OFDM. In OFDM, you have many subcarriers. Some are used as pilots, some are used for data. And towards the end, you don't use them because everything is going to overflow. Even the middle ones are going to overflow, but the end ones will overflow into somebody else's domain, and that is considered bad, and that is regulated. So the end ones are generally used as guard. Yeah, that's all it is shown here, and those are the words, right? And then, okay, that's all. And basically, this 11A was 5.4 gigahertz. It didn't become popular because it was just 5.4 gigahertz. Actually, 5.8 is the right word, but people use 5 gigahertz, 5.4 gigahertz, 5.8 gigahertz. We saw that band. Different naming. Then G came about, and G did the same thing, with the same thing except in 2.4 gigahertz, and then it became very popular. And the advantage of 2.4 gigahertz was that now you can go back to the old devices and talk to them CCK, the complementary code keying, whatever that is, right? So B and G are more compatible than B and A. A will have to switch the band. B will not have to switch the band.